value theorem for derivatives, there's always this obligatory story that's used, and it goes something like this. I set out from Laramie. I was driving to Cheyenne, and it's a distance of about 50 miles. As I was leaving town, I passed this patrol car on the interstate. I didn't worry. I was doing under the speed limit, and he looked at me, but he didn't do anything. He just, looked and just waved me on. I kept going, and I guess on the way toward Cheyenne, I let my foot push a little bit more and more on the pedal. So I was probably going pretty fast. But then when I got towards Cheyenne and approaching the city limits, I slowed down. And coming into Cheyenne, there was another patrol car. And this guy saw me, and just as I passed him, he flashed his lights and pulled me over. And he talked to me, and I said, "Officer, I was doing under the speed limit. Why did you pull me over?" And he explained that he had been on the radio with his friend, the other patrolman, who was in Laramie. And by comparing notes, they said, well, this guy drove 50 miles in 35 minutes. So at some point during that drive, I must have been going over 85 miles an hour. So this is a patrolman, highway patrolman, evidently, that had taken a calculus class. And here is how he made that deduction.
The mean value theorem. Actually, this is the mean value theorem for derivatives. Later in calculus, there's a mean value theorem for integrals as well. This is the one for derivatives. And here are the conditions, first of all, under which you can apply the theorem. You need to start with a function that is differentiable. Well, it's differentiable on the open interval because normally we don't talk about differentiability at endpoints. That would require talking about one-sided derivatives, which we won't get into. And it's also continuous on the closed interval. We know what it means to be continuous on a closed interval. At the endpoints, you've got this one-sided limit, which agrees with the value of the function at the endpoint. Now, at the interior points of the interval, this looks redundant because, of course, at an interior point, if it's differentiable, it's also continuous. And the reason we're stating the theorem this way is to clarify that we have this stronger condition as well, that the endpoints. Now, let me remind you that mean refers to average. The average rate of change of the function on the interval is the change in the function divided by the change in x. So that's the slope of the secant line joining the endpoints of the curve. And calculus relates the average rate of change over the entire interval to the instantaneous rate of change at some point of the interval. The theorem says under our conditions there exists an interior point at which the instantaneous rate of change agrees with the average rate of change of the function over the entire interval. So graphically, it means if you have this point, this interior point C, the slope of the secant line is the same as the slope of the tangent line. Let me go back to the example driving from Laramie to Cheyenne. It's a distance of 50 miles, which I claim to have been able to do in 35 minutes. Here's a distance time plot for my trip, where I start off at time 0, distance 0 on my odometer. And as the trip starts during the first 10 minutes or so, I'm just speeding up, so I'm not going very fast. That's why the curve is more horizontal looking toward the beginning. And then it gets steeper in the middle. That's because I'm going faster. And the curve levels off. That's because I slow down when I approach the city limits of Cheyenne. At any point of the curve, the slope of the tangent line is the instantaneous speed. That would be the speedometer. The average speed over the entire trip is total distance divided by total time. It's about 85.7 miles per hour for the entire trip. Now, the theorem says that there must be some point where my instantaneous speed, what the speedometer actually says, was 85.7 miles per hour. And from this graph, you can see the likelihood, at least, that there were more than one such point. In this case, there are at least two such points, and I've marked them. And graphically, what it means that the slope of the tangent line at each point, and that's the instantaneous speed, is the same as the slope of the secant line over the entire interval, the average speed. So there can be more than one point, C, that satisfies the conclusion of the theorem. Hand in hand with the mean value theorem, we have something called Rolle's theorem. It looks very similar. Actually, it is a special case of the mean value theorem. This is the special case where the function, in addition, happens to have value 0 at the two endpoints of the interval. So my function is differentiable on the open interval, continuous on the closed interval, and at the two endpoints, the value is 0. So now the average rate of change of the function over the entire interval is 0. And the conclusion is, as before, that there's a point in between A and B, an interior point, where the instantaneous rate of change is also 0, the same as the average for the entire interval. So graphically, what that means is you have a point where the tangent line is horizontal. And once again, this does not have to be a unique point. There could be 2 points or 3 points or many points, infinitely many maybe. And you might look at Rolle's theorem and say, why do we need to talk about Rolle's theorem if we already have the mean value theorem? Well, the answer to that is twofold. One is that there are a lot of special cases where you really just need a function that has average rate of change 0, and this is all you really need for that. But the real reason why we have Rolle's theorem, it's a mathematical one, is that this is the one that you prove first. If you're trying to prove the mean value theorem, it's easier to prove this special case. And then from this special case, Rolle's theorem, you can easily conclude the mean value theorem as a consequence. And the argument is just by subtracting off this well-chosen linear function from your original function. Your textbook probably goes through this argument to see why Rolle's theorem and the mean value theorem come out to say the same thing. Rolle's theorem is a little simpler, but from it you can get the full generality of the mean value theorem.
The statement of the mean value theorem should look very natural and intuitive, but how to prove it is another matter. It's a question of relating the local properties of a function to the global properties, relating instantaneous rate of change to average rate of change. So they become non-trivial applications. In the second video, we'll talk about applications to testing for a function to be constant, to be increasing, to be decreasing.